Here we go. 2.1. Functions are not differentiable at jumps, vertical asymptotes, or oscillations, which are also not differentiable at sharp turns or vertical tangents. Let's examine the vertical tangents idea. Let f of x equal x to the 1/3 power. Of the derivative, define the derivative at x equals 0. Find the derivative using the limit definition. So the limit as delta x approaches 0, limit as x approaches 0. So we're going to have x to the 1/3. Remember what we can do with powers. X to the first is the same as x to the 3/3. Subtract the exponents. 1/3 minus 3/3 is -2/3. So you can look at it like that, but it's going to be more helpful to us, exponent that's really in the denominator, or it's going to be more helpful for us to look at it like this, because then now we can, sorry, this isn't delta x here. This is just x, the limit, so we don't care if it's positive or negative infinity. It's just that that limit does not exist, so there's no derivative. So any function with a vertical tangent or a cusp will not have a derivative at the place where they have a vertical tangent or a cusp. Let's talk about how to graph the derivative on the graphing calculator. First of all, you want to go to y1. You know, y1 equals, or 1 equals n deriv parentheses. Now what you want to do is put the function that you're trying to graph the derivative of. So let's say we want the derivative of 2x. So you'd put 2x there. Then you have to put an x here. X, this value right here is always what variable you're taking the derivative with respect to. So with respect to x. And then here we want it not the derivative at a certain point like we talked about yesterday, but the derivative at all x values. So we put x there. Fortunately for you, you can't go to your home screen and type this in and have it give you the function of the derivative. You're going to actually have to calculate that yourself using the limit definition. So this will throw the graph of the derivative of 2x in your graphing feature. So when you hit graph, and then graph, and it should be a straight line at y equals 2. Because the slope of y equals 2x is 2, and derivative is the slope of the tangent line, and this line is a horizontal, or this line here, y equals 2x, will be the slope of 2. So it should be a line just going straight across at y equals 2. But that will work for any function, anything other than 2x. You could graph the derivative of x squared or x cubed or whatever. In order to determine what the graph of the derivative of a function is, based on the graph of the function though, you're going to have to know a little bit more than just how to use your calculator. Slopes, and approximate those slopes and then use them as y values. Let me explain. So let's look at this function f of x equals 3x. If we look at different places on the graph, at the tangent lines, I have the spinning wheel here, okay. Look at the tangent lines at different places on this graph. They're going to be all in a tangent line at this graph. It's going to be, like if I find the tangent line between here and here, it's the slope of about 3. Here, 3, here, 3. Everywhere I'd have a slope of 3. So what we're going to do is, when x is 0, here's 0, what's the slope right there? It looks like 3. So we're going to, what about at 1? Slope looks like it's 3. Put a dot at 1, 3. So our x values are still the same x values we had from up here, but our y values are actually the derivative values, the slope. So x is x, but y is the slope at that value, whatever x is. So if we look at -1, the slope there, no matter what x value I choose, the slope's going to be 3. So if I want to graph the derivative, it would look like that. Well, sometimes in the AP test, they don't give you the function. They just give you a picture. So that's why we're analyzing the graphs and trying to find the derivative graph. What you'll have to do often is match the with its derivative or match the derivative with its function. So you have to know the relationship between a function and its derivative graph without even knowing what the function equation is. So like this is the graph of x plus 2. But let's say we didn't know this was x plus 2. We'd have to approximate the slope. So let's look at the point 0. What's the slope there? 1. What's the slope at x equals 1? Tangent line looks like it would have a slope of about 1. So everywhere you go, -2, the x value is -2. What does the slope look like? It looks like 1, so that's going to be our y value. So the graph of this derivative would just be a horizontal line at 1 because everywhere here, the derivative of this graph is 1. Let's look at more complicated ones. Graph of x squared. We all know it's a parabola, right? Let's say we don't have the function, so we can't calculate the actual derivative. Let's look at certain values. At 0, the slope of the tangent line looks horizontal, so 0, 0 is a point. How about at 1? Slope of the tangent line looks like it's about 1. So over 1 up 1. Our y value is the slope. What about at 2? That looks pretty steep. 2 is maybe 3 or 5. Let's say it's 5. So that's our slope right there. Let's talk about over here. Tangent line slope looks like about -1. So -1, -1. How about at -2? Pretty steep, but again, negative slope. So maybe -5. It's probably here. So these are just approximate. I know the graph of the derivative should be a straight line. So when x is 2, the slope's probably 3. When x is 2, the slope's probably when x is -2, the slope's probably -2, -3. Ugh, can't talk. When x is 2, the slope is probably +3. When x is -2 here, the slope is probably -3. So these, if we draw a connecting line with all these slopes that we've approximated, we can see that the slope of the derivative is about a straight line. X squared plus, whoa, what did I do there? That's supposed to be x squared plus 2 is 0. At 1, slope looks like it's about 1. At 2, can't even see it, it's pretty vertical, or almost, we'll say it's 3. -1, we're just approximating these slopes of the tangent lines. Okay, let's look at one that's a little more complicated. How about absolute value? At 1, the slope is 1, so 1, 1. At 2, the slope is 1, so 2, 1. 3, the slope is 1, 3, 1. What's going on at 0, though? Can you find the slope at a sharp turn? No, we would have nowhere to put that. There can't be a tangent line at a sharp turn, right? So there's no value here. How about at -1? The slope's -1. How about at -2? Slope's -1. -3, slope's -1. So this goes like this, hits here, open circle here, all across. Because at 0, it's not differentiable. So we won't have a derivative there. The graph of the derivative does not exist there. How about 2 times the quantity x minus 2 in absolute value? Again, here it will not be differentiable. So at 2, we're going to have an open circle somewhere. What's the slope of the graph at 3? Looks like it's about 2. 4 is 2. 5 is 2. It's going to be 2 all the way, but not right at 2. So until 2, it's -2. So the graph of the derivative of absolute value functions it's a piecewise function based on the slope. Cosine. Here's a nice easy point. Slope there looks like it's about 0. So 0, 0. At 1, maybe -1. So 1, -1. At 2, maybe a little bit steeper. Let's go this way, -1. looks like it's about positive 1. At negative 2, maybe positive, I don't know, a little bit higher, a little bit steeper. Negative 3, back to 0. Approximating. So if all you had to do was match the derivative and its function, you would just examine different points and see if the points matched up with what you thought. So 0, slope of 0 here, y value of 0 here. Slope of negative 1 here, y value of negative 1. So that's what you're matching up. How about cosine x plus 2? It's going to be the same thing. 0, 0, 1, looks like it's about negative 1. So it's going to be that same thing. Just because we translated it up doesn't mean that the slopes change. Okay? Graph of f prime of x of this one, it's about a negative 1 for the slope. 1.5, negative 1. At 3, it's like negative, I don't know, negative 0.5. At 1, it's pretty steep. So if you've got more and more of those, it's going to look like this. And if we go over here, negative 1, it looks like it's about negative 2. Negative 2 looks like about negative 1. Negative 3, flatter, like maybe negative 0.5. That's going to go like this. The more points you choose, the more accurate your graph will be. But that's the graph of the derivative of this. So derivatives look kind of cool. Just be sure you know how to match a derivative with its original function graph. All right, derivative. So remember, the derivative is like slope. So if I'm trying to find f of 3 and f of 3.1, first of all, I plug them in. So f of 3 is 9 times 4, which is 36. F of 3.1 is 3 times 3.1 values. So we're finding the slope between 336, that's the first point we got when we did this one, and 3.1, 38.13. So y minus y, y2 minus y1, over x2 minus x1. So that is 2.13 divided by 0.1, which is 21.3. So we're approximating the derivative of that function at 3. That's one of the problems on your homework. I just wanted to make sure you were aware of how to do that. All right, there we go. We're ready for homework. Class on Monday, October 1st. Have a great weekend. Or hopefully, maybe you already had a great weekend. Maybe this is Sunday night. Anyway, we'll see you Monday morning.